Hello and welcome to today's IWCS webinar. My name is Connie and I'll be the Cisco WebEx producer for today's event. Now I'm pleased to turn the webinar over to Ed Fenton, your IWCS moderator. Ed, please go ahead.
Thank you, Connie. Our IWCS webinar series event is hosted by the International Cable and Connectivity Symposium. I am Ed Fenton, a cable industry advisor working with the IWCS team. As Connie said, if you have questions, please use the Q&A box on the bottom right of your screen to post a question anonymously at any time during the presentation. If you wish to contact the presenter or IWCS after the presentation, you will be given the contact points at the end of the webinar. Please note that IWCS does not distribute the presentation slides from either our conference sessions or these webinars. However, please feel free to contact the presenter directly and they will respond individually to you. Today, we welcome Dr. Paul Brigandi, Application Development Leader, Dow, in Pennsylvania, USA, who will be presenting his paper on accelerated heat aging of data cable insulation materials for Power over Ethernet, PoE, applications. Dr. Paul Brigandi is Application Development Leader for the Telecommunications segment in the Dow Wire and Cable TS&D Group based in Collegeville, Pennsylvania. Paul earned a PhD in Polymer Science and Engineering from Lehigh University and a BS in Chemical Engineering from the University of Delaware. Prior to this role, Paul defined the global strategy and technical roadmap for various wire and cable platforms and led compound and application developments in power distribution and transmission segments. Paul is a member of the Society of Plastic Engineers, Lehigh Valley section, and serves as the Counselor Secretary and on the Board of Directors. Paul, we welcome you to present at today's IWCS webinar series event.
Thank you, Ed. Good morning, good afternoon, good evening. I appreciate everyone taking the time on this Friday to join this presentation on accelerated heat aging of data cable installations. And we're particularly focused on these areas from the standpoint of the emerging Power over Ethernet applications in the marketplace. So today I'll walk through a little bit about our motivation for this work, go through some of the accelerated heat aging studies that we did spanning measurements such as oxygen induction time, mechanical property measurements, and ultimately looking at ways to model estimated service times in the in-use applications. And we'll look at various comparison of the data for OIT as well as the mechanical properties and best way to look at these materials and be able to model your given systems. And then we'll wrap up with some summary and conclusion. So this is something that I won't have to really spend a lot of time on with this audience, but obviously the Power over Ethernet provides simultaneous transmission of data and power over the same twisted pair cable. There are more and more applications demanding the need for more power as we see the trend going up from 15 watts in the initial stages, now talking about movement up to 100 watts and potentially beyond as more and more devices are connected to these networks and the Internet of Things, not only for consumers, but also in industrial segments and other areas, demand more power and data for various applications. And as we talk about power and data transmission, what we're really talking about in terms of the materials is that the need for the power is going to drive heat generation within these cables. So typically data cables are not subjected to significant heat generation when just data is transmitted. But when now you start talking about power over the copper conductor, the resistive losses cause the heat to generate And as you go to higher watts, you have higher heat generation, which in turn brings about different needs for both the cable and ultimately the materials that are used for different applications. So when we talk about this, we're really focusing in on the material advances to look at addressing this heat challenge. So as I mentioned, the heat generation brings about the potential risk for thermal aging of the polymer insulation itself, signal loss, as well as safety concerns when you talk about installation and in-use applications. So there's a number of different strategies that are looked at to mitigate this risk. One is the cable design. So generally, when you talk about the cable design, the conductor size is one of the leading ways to mitigate heat loss or heat generation. So where traditionally you had smaller gauge copper, as the need for more power arises, movement to larger conductor gauges helps minimize the amount of heat generated, but you'll still have heat generation. And as well, you're looking at wanting to minimize the increase in cable diameters. So there are limits to the amount of, to the size of conductor gauge that you really can use. As well as looking at metal shields, but with that, there is desire to be able to work without additional layers of metal armoring and shielding. The installation, so when we talk about installation of data cables or power over Ethernet cables in particular, the one thing that's considered is the bundle size. Typically, these are bundled together in plenum spaces or riser spaces. And generally, TIA has set limits on the amount of cables that can be put into a bundle. And as you can imagine, as you bundle more cables with ever-increasing temperature rise across each cable, the entire bundle temperature goes up much quicker. And the temperature rating is another factor, given the design of the cable and use application. But we'll focus on today is really the material construction. So use of highly thermally stabilized polymer materials that can help ensure long life and reliability of these systems as we look to the future. And really within the material development, you can have things like temperature resistance of the actual polymer materials. You can look at the formulation design, such in this case, we'll kind of talk about more the thermal stabilization of these materials, and ultimately use accelerated aging conditions to predict service life operations in a conservative manner based on those material developments. So now we'll talk a little bit about the studies that we did. In particular, we looked at 3 different compounds commercially available on the market, where the real difference is in the additive package. So again, looking at the thermal stabilization, where compound A was a high-density polyethylene with a standard additive package. Compound B had an advanced additive package, and compound C actually an advanced additive package plus an adhesion promoter package for better bonding to the conductor. In this case, we did use wire samples. So we extruded 2 different cables, one on a typical 24 gauge wire with a thinner 6.5 mil insulation thickness, and also a 22 gauge wire, more typical of your higher category cables, with a higher insulation thickness of about 21 mils. We selected 3 different temperatures to run the accelerated aging conditions. those being 100, 105, and 115 degrees Celsius. And as I've mentioned, really we monitored the oxidative induction time and the mechanical properties after aging. So the first thing we'll look at is the OIT data that was generated. And what we found, similar to things that have been put out there in literature, is that the OIT actually has a strong fit to an experimental model, or an exponential model, I should say. Here we're looking at oxidation induction time at 200 degrees Celsius on compound B, the 22 gauge wire for simplicity. All other compounds and wire gauge followed a similar trend, but what we'll cover throughout this next portion of the presentation is really focused on compound B 22 gauge wire with 21 mil wall as a representative example for the others. And what we're showing here is the OIT value on the y-axis versus aging time. Aging at the different temperatures being 115, 105, and 100. The OIT was measured on the wire samples with the copper conductor included. So what you see is an exponential fit to the data out to, in this case for 115 down to 100, up to 5,000, 6,000 hours of aging time, and the drop in the OIT. For the OIT measurements, we considered a 5-minute time as the failure point when we look at the data and ultimately try to model then the predictive behavior, which we'll talk about. So based on the data that I just previously showed, we can use the well-known Arrhenius model for a lifetime prediction on polymeric materials. And what we can do is ultimately take the OIT data that we fitted to that exponential fit previously, and we're able to back out the RD value, which is really the rate value at a given temperature of aging time. Once we have our RD from the exponential fit, we're able to put that into the Arrhenius equation and fit, again, another model where natural log of RD with respect to 1 over T in the given aging time, where we then are showing the equation similar to the Arrhenius, in which case now we're able to translate that information and fit it back into that exponential model to ultimately determine a predicted service time. Now, in this case, we're taking that natural log of RD and that rate and calculating it out now for the aging temperatures or rated aging conditions that would be typical in the marketplace. So where today's cables are generally rated 60, 75, up to 90 degrees C and beyond now, as we talk about power over Ethernet, we're able to use this model and calculate the different parameters, which ultimately leads to predicted service times under any given aging temperature, where our OIT naught was the original OIT value of the given material without any aging. And as I mentioned, for OIT in this case, we used 5 minutes as a, quote, failure time. And when you put it all together back into the equation, at 60 degrees or 75 degrees for a rated cable, again, given that this is a conservative estimate of operating temperature or temperature environment that this cable would theoretically see, in a consistent manner, you're still talking about predicted service times of well over 50 years under today's environment. Now, as we look ahead at 90 degrees C and beyond, you see predicted calculations roughly around 10 years, which is still very long, again, given the fact that you're talking about a continuous, let's say, 90C operation, which is not generally the reality of installed cables. But nonetheless, gives you the basis for being able to design not only the materials, but ultimately cables and meeting various estimated or desired service times for use in the field. As you can see, if you plug it in and kind of in between 60 and 25 degrees Celsius, which would be more or less room temperature, you're over 50,000 years of service time when you look at something at the lower temperatures. But nonetheless, as I mentioned, very high predicted service times for the given temperatures typically considered today. So really, that just shows you how we built the model and gave you the example of one of the materials. So now as we look overall and summarize the data with respect to the different compounds, we show how material selection will drive the performance and reliability of a system, where in this case, again, I show here the 60, 75, and 90 degree service temperature or rated temperatures with predicted service time plotted on the y-axis. And in this case, the predicted service time for all of the wires, both the larger gauge as well as the smaller gauge, are over 20 years lifetime at 60 degrees, as well as 75 degrees. And 90, they start to come together, which shows room to further optimize in the future as we start talking about these higher level power over Ethernet applications. And in this case, I am plotting the 22 gauge wire for each of the compounds, which shows compound B, where we have the advanced additive package, to be performing at a better level than compounds A or C. But as you can see, again, they kind of do come together as you start talking about these higher temperature ratings. Now I'll shift gears and talk a little bit more about the mechanical properties. Here we're focusing on tensile and elongation. In the plots shown here, we're looking at the aged elongation and tensile strength for the given 115 degree C samples. I'm showing these representative samples because actually at the lower aging temperatures, the properties remained relatively unchanged out to 8,000 hours. So a very long aging time, and the material properties remained unchanged at the lower temperatures. In this case, we were looking for a given, quote, failure time of roughly 50% loss in retention of the properties. And so what I show here is, again, the elongation as a function of time on the left axis, tensile strength as a function of time on the right, for compound B and C on the larger 22 gauge wall. And really what is important to point out is you see the difference between compound A versus compound B and C, where compound A begins to fall off around the 4,000 to 5,000 hour aging time as far as elongation. However, compound B, compound C, as I mentioned, continue out to 8,000 hours and remain relatively unchanged. with no decrease in its properties. Thus, it makes estimating a service time based on this data very difficult when you just consider the mechanical properties of these samples, because they are performing and are stabilized out to beyond 8,000 hours or significantly longer times than we measured in this study. For the thinner wall 24 gauge samples, they all performed in a similar fashion, but did fall off at shorter aging times, as you can expect from the thinner insulation layer. And we'll come back to that in a second. So when we look at comparison between the oxidative induction time and the mechanical properties, here in this case on compound A, in the 24 gauge copper wire samples, aged at the highest temperature of 115 degrees C. What we see here in comparison of the OIT to the mechanical properties is that for the OIT value, we dropped to our 5-minute point, as I said, which was considered the failure time in our study, at around 16 to 1700 hours. Now, if I tried to translate that into the mechanical properties, you actually see that at that same time period in the right-hand plot, you would not pick up that difference in the mechanical properties. So if you were to rely on one or the other, you would not be predicting the same behavior. And so it's important to couple them together if estimating or trying to estimate given service times, or even looking at performance over time, where you need to combine multiple measurements to make sure that we're accurately giving ourselves the best chance of predicting longer term performance when accelerated conditions are considered. Because in this case, as I say, 1,500 to 1,700 hours in aging for OIT would look very poor, but in reality, the mechanical properties are still very good. Now, they do fall off shortly thereafter, and what becomes difficult, especially when we start trying to talk about predicting service times, is the fact that it's very difficult to capture samples within a given deterioration on the mechanical property side. So it's very difficult to capture in this time period and know exactly when you're going to hit the 50% reduction over time without taking many sample points throughout that time period. But as far as service time and the prediction by OIT, it does provide a good correlation with the thermal aging performance of the materials. One important point to note is that there is a color change that occurs when polymers age. However, that's not always associated with polymer degradation. So in the case here, we see compounds A, B, and C on the 22 gauge wire samples before and after aging. While compound A does show slightly more color, darker color than the other two, there are other things that come into play when color is considered, such as the antioxidants and the stabilization package used. So color alone is not associated with polymer degradation. It may correlate depending on the additive package and the different studies that are conducted, but color alone is not going to be a good predictor of aging conditions and aging performance. So in summary, We looked at the thermal aging performance of the 3 insulation compounds evaluated at selected aging conditions. Here we provide a conservative service time estimate predicted by extrapolation of this accelerated aging data using the Arrhenius type model. The service times, as I said, estimated based on mechanical properties, were longer than that by OIT. That is, that the service time estimated by the OIT actually provides a conservative estimate to correlate that thermal aging performance on the insulating materials, and would be representative of more a constant temperature at the given ratings. So there is room to look at different temperatures if a given or realistic temperature of a given cable or installed bundle is known. You can actually predict then given any temperature. Again, here we just chose the rated conditions. The predicted service time for all these compounds was well beyond 20 years, particularly at the 60-degree Celsius mark, but also even the 75-degree rated mark based on OIT. And in this case, the compounds B and C, which had the advanced additive package, demonstrated exceptional thermal aging performance, which for us, we view as a way to increase the power output and higher temperature ratings for PoE applications, but also in working together with customers and you online to be able to design even further performing materials as we look to the future for 90, 105C rated applications and beyond. And so with that, I thank you and we'll take any questions.
Thank you, Paul. Yeah, at this time, we'll take as many questions from the attendees as time permits. I'll start with the first question. For 100 to 200 watt PoE applications, which is becoming the norm, what temperature rating of materials and cables do you recommend, 90 degrees C or 105 degrees C?
Yeah, that's a great question. And I would say that's kind of a joint conversation between, between the cable manufacturers and material suppliers. And it would really be based on the given application and installation, scenario, particularly if you're talking different levels of bundling, as I say, or if it's different environmental conditions, such as, let's just say an industrial application versus just a typical in building. So I think it really depends. But I do think that the trend toward 90 and 105 is there.
Okay, thank you. Next, have you measured the amount of signal data transmission degradation during heat generation that would be experienced when powering over network cables?
Yeah, that's also a great question, and we have not done that. So we are not set up in our labs to measure signal transmission of the cables over time, but it is definitely something that we can consider doing.
Okay, great, thank you. And next, how do you think these olefin compounds compare in heat aging properties with regards to halogenated compounds as in insulation or jacket?
I would say, again, it would depend on the different materials and the different conditions considered. I assume halogenated may be referring to other polymers beyond olefins. So I think there's obviously probably some difference, but we could talk specifics offline if needed.
Okay, And yes, and again, in follow-up, the three compounds you evaluated were olefin insulation materials. Can these results be correlated to flame retardant LS0H halogen-free jacketing compounds?
So, yes, right. So I would say not necessarily the results presented here, but the model and the predictive method to be able to at least provide some sort of correlation between performance for a given material should hold. So you should be able to use this approach with those given materials.
Okay, thank you. Next, when power over Ethernet powered network cables are installed in bundles, each potentially generating heat at 100 to 200 watts, is 60 degrees C temperature rating sufficient, or should the rating be higher in these applications?
In my view, I would say we would be looking at higher rated temperatures, but again, it kind of comes down to the amount of draw, the amount of temperature rise you're going to see in a given area, how well you can dissipate the heat that is generated. So there's a lot of different factors, but if you would consider, let's say, additional safety precaution with the use of higher rated cables via the higher performing materials, then there's definitely that safety factor that you can build in a given situation.
Okay, thank you. Next question is, what temperature environments are expected from the industry moving forward?
Yeah, I think in my view, I would say that it's a wide range. As more of these applications are adopted, as more devices and different connections are made, whether it's in again an industrial environment, whether it's to look at things to support the 5G deployments. I think it's going to vary, and that's where more conversation amongst everyone is definitely warranted. But again, I think there is just going to be a more demand for data in all applications. And a lot of those are going to require higher power draw as these devices become more mainstream. And particularly if we talk about actually these IoT or even as we start talking about smart buildings, different lighting, right? So digital lighting, digital ceiling. I think there's actually going to be even more of a draw for power, and potentially, less demand on the data side. But again, it just depends on those applications and what kind of situations we're going to be in as far as installation and use. As to ultimately what's going to be the power or data draw and ultimately temperature ratings of cables.
Okay, thank you. Next, what standards are there for PoE applications?
Yeah, so what we know is, I know they're evolving currently. Right, we know the IEEE has standards as far as some of the cables and some of the requirements. UL now has started to look at the limited power rating as another measure, and so there continues to be an evolution as far as the standards, which I think is part of the value here in terms of new materials, new designs. in paving the way for support of what in my view is the devices kind of driving the devices and the applications are really driving the demand on the back end. So there are a variety of different standards.
Okay, thank you. Next, does the FR package have any effect on the OIT of these compounds, and if so, how?
So in this case, these were non-flame retardant materials. If as we start again moving ahead and starting to think about these materials and their use in different applications, such as trying to bring some benefit of olefins into plenum, you definitely would consider the flame retardant aspect. I think it would have some influence on the performance. We would have to look a little bit closer at the formulations, and at the same time, I mean, the additive package still has the thermal stabilization package would still have a driving factor as far as performance goes.
Okay, thank you. Next, OIT can often be misleading because the degradation mechanisms at 200 C are often far different than they are at regular operating temperatures. Have you looked at modeling physical properties at elevated temperatures such as 125, 135, 145?
Yeah, that's a good question. So, as I said, in this work, right? Yes, fully aware. The OIT is more a conservative estimate, and it's a good way to be able to model that performance over time, and it is much beyond reality. Now, in this case, again, we actually we did not do. So I think if I understand the question right, the question was asking about lower temperatures for OIT measurement. In which case, no, we did not look at the lower temperatures because that would ultimately then just drive out the amount of time for the study and the different conditions. As I said, for some of the mechanicals, right, we were at well over 8,000 hours. Now, if you talk about actually doing some of this aging at even elevated temperatures, so mechanical properties at 130 or 125, 135, yes, that's something that can be considered as we go forward.
Okay, thank you.
But it was not included here.
Okay, thank you. Next, would you expect better aging performance from fluoropolymer insulated cables due to their thermal properties?
Yeah, I think fluoropolymers offer their own unique performance in the applications. Really, I would say it comes down to overall balance of cost, performance, and many other factors. Certainly, they are different unique materials, for this application, and do find their place.
Okay, thank you. Next, for accelerated heat aging tests for polymers to check their service life, what parameters do you think should be taken into consideration for polymers like nylon 6 to check their degradation with time because of their higher water absorption?
Can you repeat that question?
Yeah, I will. Grammatically, for accelerated heat aging tests for polymers to check their service life, what parameters do you think should be taken into consideration? The next sentence reads, for polymers like nylon 6 do you to check their degradation with time because of their higher water absorption?
Yeah, I would say when you start thinking about other materials, when we look at these types of accelerated aging conditions and approaches, there's obviously many factors that come into reality of service aging and different behaviors in the field. So there's different things that potentially can be looked at, right? So if a given material is more prone to, let's say, moisture sensitivity versus a thermal sensitivity, sure, obviously you could look at things potentially such as aging in a humidity environment at elevated temperature versus just a thermal aging. But there are many factors that could be considered, and I think you could theoretically try and use a similar model, or may need to develop a new model, but based on different aging conditions. If one polymer of interest is more susceptible to a given degradation phenomena.
Okay. Next, thickness of insulation is very important in heat aging. Is there any standard thickness for aging test?
So in this case, no, we weren't really following a standard thickness for our purposes in this evaluation. We more or less tried to mimic kind of I would say a worst case or best case as far as, again, the smaller gauge on the lower categories, that's the thin wall, the more 6 to 8 types for today. Again, that 20 gauge thick wire is being utilized. More of a heavy wall for a given application. So we didn't follow a particular standard in this case, more try to make it as realistic as we could to the accelerated aging conditions.
Okay, thank you. Next, in addition to the Arrhenius model, are there any other models to predict cable life?
I would say yeah, there probably are. That the Arrhenius is by far the most well known and well adopted in the industry that I'm aware of. But I am sure there are others in the literature. I'm just not very familiar with all of them.
Okay, thank you. And the next question might be kind of a follow-on. The nuclear industry has been using Arrhenius aging to model temperature performance of cables for decades. Have you looked at the information and standards for this type of testing?
So not specifically, but would be definitely something of interest to us. So would be wonderful to follow up on afterwards to learn a little bit more about what has been done.
Okay. And next, the questioner wants to know why the specific temperature ranges were chosen for the test. Yeah,
so we chose to go. I would say we chose a bit of a middle ground. So typically the standards would suggest, let's say, just standard heat aging is done around 100, 121 degrees C. Again, and lower for different rated temperatures. So we kind of chose the upper end of that, particularly for let's say a high density polyethylene rated at 75 typically. would be measured around 100 degrees. So we went at 100 and then up, about 15 degrees from there. Just as a starting point, again, I think different conditions now that this information is here could be considered.
Okay, last question, Paul. Do you see interest from the market for PoE outside of the U.S.?
Absolutely. We see it all around the world, actually. I know there's a good deal of interest in all geographies that we've seen, and I think it's it's more and more in maybe a variety of different context right now, but for the most part, even if somebody is really just running IP phones, right? There's a good chance that they're already utilizing PoE. Yes, we do, and yes, I think we tend to see the same trending upward movement as far as temperature and thermal resistance needs across the globe.
Super. Paul, thank you for presenting this very interesting and important topic today. Please note the contact points being shown should you wish to contact Paul after today's event. Each of these IWCS webinar series presentation events are recorded and will be archived on the IWCS.org website. It normally takes up to 2 weeks for these to be posted. The IWCS webinar series will conduct presentation events on a monthly basis. Webinar events will take place on the third Friday of each month at 10:30 a.m. Eastern USA time. Our next scheduled webinar event will be on Friday, August 21st at 10:30 a.m. Eastern USA time. Each of you will be receiving an announcement for the event a few weeks prior. Please feel free to share our announcements with your colleagues so that they can join in and register as well. For over 68 years, the International Wire and Cable and Connectivity Symposium has been the recognized leader showcasing new technologies in cable and connectivity products, processes, and applications. Our next 69th annual international conference will now take place virtually in October of 2020. Please watch your inbox, social media, and our website as this exciting information becomes available. Also, the next UL and IWCS China Cable and Connectivity Symposium will take place on Tuesday, March 23rd through Thursday, March 25th, 2021 at the Marriott Hotel City Center in Shanghai, China. Please visit our website at iwcs.org for more event details. In just a moment, you will see a brief survey so that you can provide us your feedback and comments on today's event so that we can further improve this webinar series for you. Thank you for participating, and this concludes today's event.